All right, so this lesson is actually pretty short. We're going to be talking about logarithmic functions. So we've already talked about what log is as an operation. Today we're going to specifically be talking about the graphs of functions and inverses of exponential functions, so how all of those things are related. So this should tie a few good things together. So remember that inverses, we use the f-1 notation when we find inverses. They reflect over the y equals x line, and the domain and range are going to switch. So let's look at an example of how that comes into play when we specifically look at logarithmic functions. So first, I want to just find the inverse of this function. We can call this example 1. And to find the inverse, remember the first thing I'm going to do is switch where my two things are. So this is going to say x equals 2 to the inverse. Now this is weird because what I'm looking for is stuck up here as an exponent. So because this is stuck, I'm going to need to undo that. And remember, to undo exponents, we use logs. And one thing we need to remember is that when we use logs, we generally want the base to be on the left. So I'm going to rewrite this first as 2 to the inverse equals x. So now I can do my little log loop, and this is going to say log base 2 of x equals the inverse. All right, so I can see that these two functions are inverses of each other. And if we think about what the graph of the original function would look like, this original function right here is going to be an example of growth. So remember, we're going to have a graph that looks something like starting at 1, because that's what's in the very front, multiplying by 2, so I get this growth-looking graph like this. So log is going to be the inverse of that, and actually I already have it graphed out for you. It's going to look like this. And so if we take a minute to name all of these features of this in red is the exponential function. If we go ahead and name all of these features, domain we know is going to be all row numbers. Range is y is greater than 0. I notice that I have an intercept at at y equals 1. That's my y-intercept. I have an asymptote at y equals 0. And my end behaviors, remember I have two end behaviors. So one of them is going to be positive, positive, and the other one is going to be as x goes to negative infinity, y goes to 0. So notice what happens when we switch over to the inverse function, or this log function. I want you to really see the relationship here. So a few things that I notice. The range becomes the domain. Obviously the x changes, but those two things switch. Domain becomes the range on the other one, right? What was a y-intercept at 1 is now an x-intercept at 1. Where my asymptote line was y equals 0 right here, my asymptote is now, this is the x-axis. For your notes, I would like for you to rewrite that. That is not what I meant to do. I would like for you to rewrite that as the line x equals 0. And then the same thing, the same pattern of switching can be seen on the end behaviors. These end behaviors are now positive, positive on this arrow, and this arrow is actually 0, negative. As x goes to 0, y goes to negative infinity. You can see that right there. So you should have these two mapped out. And then on the graph, for yourself, you also can draw this like dashed line, which will help you see that it is actually a reflection over y equals x. All right, in our second example, I want to talk to you about transformations. And these follow the exact same rules of all the transformations we've done before. So in this first example, when x plus 3 is on the inside, remember inside is opposite. This right here, the transformation is that this would be a shift left 3 units. And if we draw the graph or look at the graph of these, you can see, in fact, that this graph F was shifted left 3 units. Similarly, we can make notes for these bottom two examples. So I would just write each of these as a line in your notes. Plus 4, because there's no parentheses here, this plus 4 is going to be on the outside. So this would be an example of shift up 4. And on this last one, the 5 here in the front, remember fronts are not shifts, they're like stretches or compressions. So this 5 is an example of a vertical stretch of the graph. All right, we've got one more example left to do, and that is to just find inverses, so slightly more complicated inverses. So let's look at that. So this is what my equation is going to start as, and I'm going to make notes of that. First, I'm going to switch these. X equals 10 times the inverse, or to the inverse plus 1, sorry, not multiply. I see that the inverse is stuck up at the top, so the first thing I'm going to do, remember that logs are going to be inverses of exponents. And just like I said in the original, the first problem that I did, I'm going to move this x to the other side or rewrite this. So this is going to be 10 times, or sorry, to the inverse plus 1. And now that I have that written this way, I can do my log loop. So this would be log base 10 of x equals the inverse plus 1. And because this says log base 10, I don't actually have to write the 10. I can just leave it as log x. And my last step will be to minus 1. So this is going to be log of x minus 1. You do not have to put the parentheses, but I'm trying to help you see that very specifically that minus 1 is going to be on the outside. All right, one more of those quick examples. Same idea. We're going to switch these. So x equals log base 7 of the inverse plus 5. Because I have log, I want it to be on the left, so I'm going to rewrite this. One thing you'll see me do in the future is just scribble that out and move the x to the other side. Now I can write the loop. So this is 7 to the x equals the inverse plus 5. And now I can subtract 5 from both sides. So the inverse is going to be 7 to the x minus 5 equals the inverse. And just one last quick visual for you. These are those two graphs. Draw them if you want to. Don't if you don't, I guess. But I just wanted you to see that they are actually reflections over this line. If you were to graph them, you could more easily see that. And there's no tricks to that. That's actually all we have for today.